Great. All right. So, hello, everybody. My name is Adam Radnitsky. I'm one of the co-founders here at Tangram Vision. I'm here with Jeremy Stewart, who is one of our lead engineers. Um, Today's webinar is on a topic that is near and dear to many roboticists' hearts. A lot of robot platforms use depth sensors, and a lot of depth sensors aren't exactly designed for robots. And so as we speak with roboticists, we find out more and more that many are trying to build their own depth systems to fit their specific application. And so Jeremy is going to talk in depth about what it takes to build stereo depth from scratch. And with that, I will hand it over to Jeremy.
Thank you, Adam. I assume everyone can see my slides here. I am just trying to make sure that I can resize the chat so that it's in view. Excellent. So, hi, I'm Jeremy Stewart. I'm Senior Perception Architect here at Tangram Vision. What that largely means, in practice day to day, I tend to write software. And while my day job is writing software and sort of my background is in integrating these deep multi-sensor systems. So I did a lot of photogrammetry in my education, but in particular, my sort of previous job, many people at Tangram have sort of been at this job as well. I worked at Occipital, now Structure. And I helped develop some of their Structure cameras. And in fact, I was working on sort of maintaining and supporting the calibration aspect of the production line, as well as some of the other software aspects in manufacturing a sensor. And so I have a little bit of insight into this, and I want to share that with everyone here today. And so feel free to place your questions in the Q&A. I will try to field them as best break at the end of the talk to kind of address questions more broadly. But with that said, let's get started. So the first thing I wanted to say is just a pure disclaimer up front. Nothing I say during this webinar or during this talk is an official endorsement or a criticism of any particular company or product or modality. There's a lot of variety in sort of the sensors that are on the market today. And, we've used a lot of them here at Tangram. We've seen a lot of others use them. We're not trying to knock anybody down by saying any of the things we're saying here, but there's a lot of trade-offs in this space. And we just want to make it very apparent what those trade-offs are and where they kind of arise. And so I guess the first question you might have is like, roll your own depth. Like, why would I make my own depth sensor? Or why would I make my own depth camera? And it's a pretty niche question, right? Like you have to be developing something pretty special to decide that you want to develop all of the sensing systems yourself from the ground up. And today I want to kind of go through some of the discussions that we've had with customers and talks that we've seen with companies in the real world that are building their own depth for some reason or another. And so the sort of main answer to this entire talk is that depth sensors don't always perfectly fit the bill. We try to pretend that, you have like these off-the-shelf things that you can kind of slot as modules into our systems. But in practice, it's not always true that it is the case that you can do that. It might be that your baseline is wrong. It may be that you don't need a color camera or some other variety of factors. And so let's go through some of those because we've talked with a lot of people, and especially we've talked with people who have sort of built their own systems. And as they were building their own depth system, these were some of the things that they've tried that they found out weren't very useful. For starters, the wrong baseline. So, showing this camera off right here. This is an Intel RealSense D405. It's about the size of a golf ball. It's a very tiny camera. It's got great near range accuracy. You can get really up close to objects. This is a very good camera if you're trying to scan something from a very short distance. However, that baseline doesn't work when you want to get, beyond a meter. So if you're starting to measure objects in sort of the 1 to 5 meter range, you're kind of unable to use that sensor. And so we kind of look into sensors like this. You have Structure Core, your Luxonis, your other Intel RealSense like the D435s, or rest in peace, the L515s. These are general all-purpose designs, and these are kind of what we think about when we think about off-the-shelf depth sensors. And so when it comes to these, however, they also fail because these baselines are, again, kind of fixed to a single position. Most of these cameras, although there's differences between manufacturers, are using very similar baselines or have very similar. Don't always fit the bill. If you're trying to get sort of a combination of depth ranging at close and far distances, these aren't going to cut it. And then there's, sort of the upper end options of all these cameras as well. Something like a Stereolab Z2i. This is best used in outdoor environments as kind of a proxy to getting like a full LiDAR system, like a Velodyne or an Ouster. These work incredibly well under certain conditions. But then you start to ask questions about like, what are we trading off for this wider baseline? And even with this wider baseline, if you want to get anything close, the minimum distance that this camera can generate depth at is going to be much larger than something like that golf ball size D405. And so you can see that there is a variety in choices of like what baseline you might want. But even knowing that, this baseline between these cameras is going to be tailor set for a certain profile of what distances you need or what depths you need. In addition to that, a lot of these cameras tend to use 1 megapixel cameras. They have limited resolution, and you're going to often find that these optics are on the cheaper end. In particular, when you're looking at, the sort of $400, line that kind of RealSense sells at, or something in that sort of sub $10,000 range, you're going to expect that you're going to have, plastic lenses, which will end up, capitulating to thermal effects when running the sensor, or even, just poor optics in general, whether it's a lack of an IP67 rating or, there's a lot that goes into these optics when these sensors are developed, but those don't typically have your application in mind. So if you do need extremely high precision or extremely high accuracy, and you're trying to aim for sort of the best possible like source images to produce depth, these aren't always going to fit the bill. In addition to that, we talked about lenses a little bit. I mentioned that they'll have a lot of thermal effects, but also field of view is often limited with smaller baselines and optics. So, you may have some application where you need to see, 120 degrees field of view in front of you, or perhaps 180 degrees, or maybe you need a full 360-degree view. Many of these cameras right off the bat aren't going to be able to support that. They don't use wide vision lenses. They tend to use pretty standard field of views on each of the cameras. The depth generation itself is sort of a subset of the total field of view of all the cameras. And so what ends up happening is that you need to buy many and many of these devices per unit. So you might be buying, 8 or 9 RealSense, or maybe you're buying 4 RealSense to get perfect coverage or something like that. And what this ends up leading to is kind of a price point problem where, at scale, if you're buying $400 to $600 a sensor, and that sensor isn't really tailor-made for your application, can't be customized to your needs, and imposes a lot of other things downstream on your project, it's also important to remember that this is a decent amount of your bill of materials. And so if you've got 4 or 8 sensors, you can very quickly, make the baseline price of your robot $2,000, $4,000, etc. And while having a vision powered service is often desirable, this can be a non-starter, especially if you're trying to keep your bill of materials low. In addition to that, we now need to talk about sort of the other half of cameras. It's great to talk about the hardware. Maybe you can be happy with something that you found off the shelf, or you know what meets your needs. But then you go to plug it in, and you're now forced to use the manufacturer's software. Uh, and let's face it, most of these sensors are developed by hardware companies, and it shows. And that's not to like kick down on like hardware companies as being sort of less advanced. It's just that without high quality software experience, you tend to end up having to put in more and more work over time to make sure that these sensors are operable, always running, providing good data, etc. And so, especially in some cases like LibReal Sense, uh, you know, we notice and we hear a lot of feedback that it's very hard to integrate these things. And so there's a lot of instances where folks will decide not to use a camera purely because the software experience is so bad, because they have an entire engineering team dedicated to making it work, and yet it still just is not suitable for purpose. So let's say you buy my arguments and you say, okay, I don't want any of these off the shelf things. I have some idea of kind of where I want vision on my robot or on my platform or on my system, whether that's pick and place or warehouse robotics or some sort of outdoor or ADAS application. What am I even doing? What kind of questions do I need to ask myself? And like, how does one even get started thinking about that? And so we're going to talk about kind of both aspects of like both the hardware and the camera selection itself, but also the software. And I'm going to touch on that a little bit more at the end. But to start with, for camera selection, we have a variety of topics that we probably want to ask ourselves about before we even get into the project. One of the things with hardware is that the choices that you make early on are going to affect your project and really drive what development looks like years down the line. And these are things that you need to make decisions on very upfront that you're not necessarily going to be able to undo easily later. And so that includes market availability, spectrum, shutter type, et cetera. You can read them here on the slide. I'm going to go through each of these independently and kind of give you an idea of one, how they interrelate with each other, but two, why we say that like making these decisions up front is very important because they do tend to shackle you down the line. So let's start with the obvious one, market availability. We're still in a constrained supply chain world. A couple years after the pandemic, components have not been easier to get. Many of the most available cameras are also used in a lot of other industries, which is good and bad. You have cameras that are used for smartphones, ADAS systems, so advanced driver assist systems, and other consumer devices, generally speaking. When you're picking your cameras, just keep in mind that exotic specs will introduce some risk into your supply chain. One of the things that's really important to consider is that your supply chain needs to last for sort of the lifetime of your device, which sounds a bit weird, but if you're still speccing out the hardware and you're in that very first iteration of that, or very first stage of that iteration, you haven't shipped anything yet. And so if you expect your robot to be, V1 manufactured with a certain hardware configuration for 5 years, you need to make sure that you have 5 plus however many years of development available for your supply chain. And so oftentimes the smart choice, especially when looking at a constrained supply chain space, is to sort of figure out what other products exist in the market that use the camera or that have a similar spec to what you're doing, and to just buy a similar product that falls along those lines. That way you have an idea that that product will long-term be supported for something else, whether that be a smartphone or a consumer device. And so you don't have to worry about, your camera manufacturer telling you 2 years into production that, hey, we've discontinued this entire like product line. We don't have anything to replace it. And that's something that would impose a huge risk into the system and something you don't want to deal with, 3 years from now. So when you find a camera you like on AVNet, Mauser, or like DigiKey or something, try to validate that like you have some long-term availability by matching it to whatever mass-produced product is primarily used for. So you might find, like, for example, like the Sony IMX390, it's a popular choice for ADAS systems. And so if you're looking for sort of the lifetime of that, you just need to figure out like what ADAS systems is this being installed into? What is the product life cycle? Is that expected to be, 5 years of support and warranty? Is it 10 years of support and warranty, et cetera? And you can kind of tie your idea of what market availability you have to that. Moving beyond sort of the supply chain itself, which I'll admit is kind of my weakest aspect of experience in this space. Let's talk about the spectrum. Typically, you'll have like some sort of electromagnetic spectrum that you need to target with your camera. And this could be, typically it's visible radiation. So you're in this sort of middle space where there's visible light and sort of near IR, which is this sort of early IR space that's close to the visible light region. The reason for this is because those cameras are actually much cheaper and easier to manufacture, but also how do you make that choice? What kind of camera do you want to make? So let's talk about the spectrum a little bit. First, we'll talk about RGB. One of the pros of RGB, especially if you are choosing to build a depth camera or a depth sensor, is that by adding an RGB camera, it's like completely necessary if you need photometric information in some way. If you're trying to do RGBD or some sort of like colorized depth, you're going to need an RGB camera of some kind. And this is useful for different machine learning pipelines. It's useful if you're trying to find texture or contrast within a scene. And so this is a very flexible thing that's kind of embedded in sort of the computer vision space. However, there's some cons to it too. First off, this relies on the visible spectrum. It seems dumb to say it, but if you build a camera that's based off of visible light and there's no visible light, my common example is you have a robot, it's in a factory, you want your robots to be working 24 hours a day, but when the humans get off their shift, they turn all the lights off in the factory, your robot doesn't work anymore because there's no light. And so this is a risk that you have to consider. What kind of environment are you operating in? And is RGB something that's viable for that environment? In addition to needing visible light itself, there's a bunch of effects that come out of sort of the debayering process of an image. So if you're familiar with computer vision or not, the sort of rough tutorial is that the way that RGB data is captured in an image, there's red, green, and blue pixels. And by interpolating sort of a combination of certain pixels, we're able to derive or more correctly interpolate a red, green, and blue value for every pixel location on the sensor. This kind of comes with a couple of different caveats, though. That debayering process, in addition to other sort of pre-processing steps that go into image generation, can result in things like chromatic aberrations, moire effects being this sort of like, rainbow colory, sort of wave looking thing that you can see on some of these images as the color bleeds out of its space. You get this false coloration, etc. You might need to do some sort of temperature balancing or white balancing on the actual whites and colors in the scene in order to get a good color profile. And so there's a lot of work that goes into making a good RGB camera. You can't just slap a sensor onto, a board and just hope it streams everything correctly. There's a whole bunch of pre-processing steps that happen before that. And so, with all of this said for RGB, there's one other option with visible light that we can take, and that's grayscale. And so unlike RGB images, with grayscale, there's no debayering. And so there's none of that interpolation step. So we don't have to worry about chromatic aberration or moire effects or whatever. It's just purely an intensity image of visible light. And so if you know that you need to work with visible light, but you don't need the color information itself, the grayscale can be an excellent choice because you get much sharper imagery. You don't have a debayering process, and there's, as a result, less bandwidth required. You're not sending a red, a green, and a blue value down the channel for every pixel that you get in your image. And so as a result, you get higher data throughput. You're just sending an intensity value. The cons, obviously, no photometric information. If you really, really need RGB, then you need RGB. The problems that I mentioned in the last slide are something that you still have to tackle. And lastly, this still relies on the visible spectrum. So if somebody turns all the lights off, it's not going to work. As for sort of an example of sharper imagery and how this doesn't happen in RGB, I'll go back to this slide real quick. The top right image, you can see this black line kind of drawn as sort of an edge on this concrete. And there's the false coloration in it too, but that line gets much wider as it goes up the side of the image. And some of that is due to, the actual natural topography of the scene that we're capturing. But the other part of that is that because we are doing this interpolation, that edge is not as directly observed because there is that debayering process that's constructing this edge. And so this false coloration kind of demonstrates that we get this line in our image that's much wider, even if just by a couple pixels, than we would normally expect it to be in a grayscale image. And so when you're using grayscale, that's something that doesn't happen. And that's something that can be a real advantage if you're looking for very high resolution imagery, which can be useful if you want very dense, very continuous geometric resolution in your depth frame. And lastly, let's talk about infrared. Infrared is kind of nice because unlike visible light, it's robust to lighting conditions. So the day-night cycle doesn't matter. You don't need to have lights on, or at the very least, you don't need to have visible lights on. And so if you're building something that's interoperating with humans, this can actually be an advantage. One of the things to talk about with infrared is that most cameras that you see that are off the shelf today will be using infrared for the actual depth generation itself. This is a function of the fact that many of the block matching algorithms or many of sort of the depth generation algorithms that we use to generate a depth map will rely on infrared plus some IR projector to produce a very consistent, repeatable pattern within the scene that we can then use to derive depth consistently in every frame, regardless of the lighting, regardless of the object type, of the texture, etc. And so if you are looking for building a depth camera, which is what this is about, projectors and emitters are widely available in the infrared spectrum, not always so much in the sort of visible light spectrum. Not because it's hard to make a projector for visible light, but because they tend to interfere with each other and they tend to produce very weird interference effects when you consider that, people are usually in the same space and don't like, flashing projector lights, strobing all around their workplaces. Some of the cons of infrared, though, the resolution is often limited by the CMOS pixel sizes. And so, one example of a depth sensor that I always go back to is, I'm not sure if anyone here has ever heard of the Swiss Ranger cameras. Has anyone ever heard of the Swiss Ranger camera at all? It was an old time of flight camera. You can post in the chat if you've heard of it. But the Swiss Ranger cameras were pretty unique in that in order to achieve the correct signal to noise ratio, the pixels had to be very large. In particular, they were 42 microns. For reference, a typical digital camera or a typical RGB image sensor will have pixels roughly on the size of 2 or 3 microns. And so we're looking at about a 10x size difference for a time of flight camera. And for many years, this was an actual physics problem in manufacturing to solve. How do we get good signal to noise ratio? So when you see infrared cameras on the market, you'll often see that they're much lower in terms of megapixels or in terms of resolution. For this reason is that because there's less direct infrared light and because our filters for infrared light are required in order for that to work, we are somewhat limited in terms of what the min pixel size can be, which directly affects the resolution. And lastly, other cons, this doesn't work without IR. Again, it goes without saying, it's the same problem as if, you have some robots working in a factory and you turn all the lights off, they can't see anything. That is fine if you have IR projectors because you can turn all the visible lights off. That doesn't affect the IR spectrum at all. However, Conversely, if you don't have an IR projector, or if you have way too much IR light, the classic example is taking your depth camera out into the sun. It completely washes it out, and now your camera is not generating depth, and it's not very useful. So it's important to consider that there may be failure modes to using infrared if you're working outdoors, as well if you're working in a place that has a lot of IR noise or that has to observe objects that absorb IR really well, like water, for example. Um, and the last one is just a very narrow band of info. Unlike visible light, we do have to have filters on the camera in order for IR to be observed correctly. And so there's a very narrow bandwidth of information that we can garner from that. All right. So on to the next topic, shutter type. You'll often see shutter type be listed as sort of global or rolling shutter. This is kind of a layover of how cameras kind of used to work in the analog sense, where a shutter would roll and you'd have sort of a left to right readout as the shutter kind of opens and closes in sort of a rolling fashion across the image plane. With digital cameras, we have a similar effect. We still call it rolling and global shutter, although it's actually more correspondent to the pixel readout. So a rolling shutter camera reads each column sequentially out from the camera over some integration period. And that readout being sequential leads to the fact that the object, if there is an object in motion and you're reading this out sequentially, then there's short delays between each readout of each pixel. And so the rolling shutter gives you this kind of weird motion artifact that you see here on the left. In a global shutter camera, all of the pixels are read out synchronously at the same time. And so by having that happen, you don't have any delay between when the pixels are read out column to column relative to each other. And so given that, you're able to actually get an image that more accurately observes motion without having to worry about this sort of rolling shutter artifact. In practice, there are some reasons to prefer rolling shutter camera, but most of the time I would recommend, at least it's my preference, to use a global shutter camera. The reason for that is that while global shutter cameras are more expensive and will contribute more to your bill of materials, one thing about them is that they solve a lot of problems downstream in the software that you may not want to deal with. In particular, rolling shutter corrections have to kind of be pushed through your entire pipeline end to end. You can't just say, oh, we fixed the image once and then it's fine. Because that kind of correction is sort of within the frame and then also frame to frame. And so, unfortunately, this kind of imposes a large software burden on your project up front that you may not otherwise notice until you get way down the line and you're building, a SLAM system or a scanning system or a pick and place robot. And now out of nowhere, you have, rolling shutter artifacts are causing this whole thing to not work. And this is why I say, like, when you pick your camera up front and you're choosing this hardware, many of the decisions you make early on aren't going to be felt until way later. And when you do feel them, you can't really go back and change that. You can't say, oh, let's just switch out for a global shutter variant. That's not a setting you can, flick on and off. It's part of how the hardware is built. And so kind of sets you back to step one. If you do really think that you need a rolling shutter, usually the justification is that you want to reduce the amount of pixel noise, which is why rolling shutter cameras are still very much in use in CV today. Although in practice, for most cameras with, decent lighting, especially if you have an IR camera with a projector, which is pretty common for a depth camera itself, for getting dense depth, that's not going to be a consideration because your signal to noise ratio is going to be plenty high enough that that's not going to contribute to the major source of error in your actual application. At least, again, prefacing that with, that's my experience, that's my preference. But perhaps you have some sort of experience of your own that required a rolling shutter camera. So let's talk lenses again. In particular, let's talk field of view. So you have picked some of your hardware, you have a global shutter camera. So you've picked your CMOS, you know what you want to do with that. The next question you might have is, well, what kind of field of view do I want to build into this depth camera? And what kind of field of view do I want on each of the individual cameras themselves? And so Tangram actually gets this question a lot. And we actually built this simulator to kind of demonstrate between existing cameras that are on the market that do this, what is their field of view? What does that say about their minimum range? What does that say about their maximum range? And so in this sort of 3D simulator, you can see what does the camera see? What is the minimum range? What is the maximum range? And you're able to kind of compare it to existing products on the market. And in fact, you can add your own custom sensor here. It doesn't have to be the PMD Pico Monstar or the Mint ID. It could be either or. And you're able to compare your actual requirements using our simulator to something that's sort of closely matched on the market. So when it comes to lenses, you've sourced a camera. You may still find that you have different field of view requirements depending on how much you want to see in a certain range, how many of these cameras you want to actually include. You have sort of an optimization problem on your hands where you want to kind of minimize the number of cameras so you can minimize your bill of materials. But if you try to increase the field of view too much, you now start to have other questions like how much distortion in our field of view is tolerable. It's we'll talk about this a little bit later, but especially with very high distortion lenses, we're looking at like fisheye lenses and such. Common disparity matching or depth map generation algorithms just don't really work. The operating principle under how they derive depth just isn't compatible with the amount of distortion that's in a fisheye lens. And so while you may have 270-degree field of view over some scene, you're still only getting a depth map within 60-degree field of view within that 270-degree subset. In addition, do these non-default lenses contribute to the bill of materials? This may be a manufacturing step that you have to undertake yourself. You may know that you want a certain sensor or a certain CMOS of some kind. However, you may also find that, even with that, there's no way for sort of the provider via, Mauser or something to get that lens on there for you right off the bat. And lastly, and this is more sort of a quality thing that you may need to consider down the line, is sort of the thermal expansion and contraction of the lens. And so when you're looking at both sort of the raw camera module itself, as well as any additional lens components that you may install in front of that, you want to consider what kind of effects will happen due to thermals. And so, plastic lenses, for example, will expand and contract a lot under different heat loads. And so if your cameras are, next to your processor or next to some hot part of the chip, that may be something that consistently happens. And you may find that there's a lot of thermal expansion in there. Additionally, if you're operating outside, whether it's hot or whether it's cold, you may see a lot of different distortion, or your calibration may not be tolerable outside of certain temperature bounds. And so when you're looking at additional lenses, it's especially important to look for like the thermal coefficient. It's usually some number, often labeled like alpha or something. You want it to be as close to 1 as possible, which effectively means that there is no thermal expansion or contraction. It's possible for that to be the case, but tends to be the much more expensive option, especially if you're buying cheap camera modules. You can expect that most of the time those lenses are going to be plastic. And so this is something that you may need to care about whether or not you have additional lenses in the mix. And then resolution. We talked a little bit about resolution. Do you want a 1 megapixel image? Do you want a 2 megapixel image? And this kind of depends on sort of the needs of your project and what you're trying to actually image and get depth from itself. Oftentimes 1 megapixel is kind of where the industry standard kind of sits at. And so that's this sort of 1280 by 720. But even then, you'll find that many images, like even the RealSense D435, will give you sort of a weird depth resolution of like 848 by 480. And that's kind of just a structure of like the fact that they are using a sub 1 megapixel pair of cameras to generate a 1 megapixel sort of fused depth frame. But that being said, more pixels aren't always better. You have compute limitations. So, every pixel you add is, effectively 4 times the amount of compute because you have sort of that width and height computation to always consider, as well as frame rate limitations. Like, if you're expecting this to operate at 30 frames per second or 60 frames per second, can you generate depth at 60 frames per second? And as you increase the resolution, you're constantly building that problem larger and larger and larger and larger every time, and it doesn't scale linearly. And so that is something that you really have to consider when you're doing this. Is it possible to use less dense depth or to use a lower resolution camera in order to get just enough depth to fulfill the needs of my application, so that I don't have to spend as much on a fancy SOM or a fancy, processor or some big chunky host machine with like several graphics cards just to make this happen. And lastly, one point I wanted to talk about is that pixel pitch matters. More pixels aren't always possible. I talked about this a little bit already about how, the pixel pitch or sort of the pixel size of something like the Swiss Ranger camera was 42 microns. So our infrared camera resolution is often limited by pixel pitch. And so it's important to remember that as these pixels get smaller and smaller, you're going to expect to see more noise, more visual noise in the image itself. And that's something that can be corrected with an ISP or an image signal processor to some varying degrees of success. But that signal to noise ratio that you're getting from the camera is always going to be bound by that pixel pitch. And so it's important to keep that into consideration when you're picking a camera, is to pick something that has a reasonably sized pixel pitch, because having lots of pixels that are very noisy isn't always better than having fewer pixels that are pretty good. We talked a lot about baseline too. And I know that I'm kind of rifling through these at this point, so I apologize at how fast I'm going. But if you do want me to pause and go back to something, please message me in the chat. But what kind of baselines has everyone worked with here? Just looking at the attendee list, if anyone wants to jump in. Bueller. So for many of the baselines, we can look at something like this sort of 1 centimeter baseline chart. And this is sort of a simulation that Tangram does to evaluate what kind of baseline do we want and what kind of performance can we achieve given a certain baseline. And so for a 1 centimeter baseline, which is pretty close to that golf ball size sensor we started at the very beginning, we want to show with this graph sort of on the x-axis is how far away is the actual object. And on the y-axis is sort of how much error in accuracy would we have if there was a 1 pixel difference in the disparity. So if you were off by 1 pixel in your disparity evaluation, how much error would that introduce into the depth? And so you can see when you have a 1 centimeter baseline, at about somewhere between 2.5 and 3 meters, you get 1 meter of disparity difference, 1 pixel of disparity difference translates to 1 meter of error in your final depth calculation. And so this is why when we see like a very narrow baseline, these are typically only used up to about 0.5 meter, because at that point, the error is somewhat negligible. And in fact, you typically want to be closer than that. Conversely, if we look at sort of a wider baseline, we do the same simulation. So instead of 1 centimeter, we have 20 centimeters. And we do that same 1 pixel disparity difference. You only get to 1 meter of error at just beyond 10 meters of distance. And so generally speaking, the farther you want to go, the wider of a baseline you want to have. But you are kind of trading that off against how close you can go. Because while you can see that this line is simulated and is very low from sort of the 0 mark to, 2 meters on the x-axis, in practice, you're not going to be able to see anything between these two cameras without an extremely wide field of view at 1 meter away. That's just because you're not going to be able to generate depth if only one of the cameras can see the object that you're trying to observe. And lastly, we talked about emitters a little bit. So say you've now figured out your baseline, you figured out your camera modules, your lenses, your supply chain to some degree. You now know that you want IR. You have to ask yourself active or passive. And so active depth is basically the idea that you have some stereo projector or you're intervening to provide some texture or pattern within the scene. And so there's a variety of ways to get that active dense depth. It could be stereo rectification, time of flight, or structured light. And so if you're doing dense depth, you pretty much exclusively are going to want an emitter. But does your application need dense depth? Because if so, you now have a lot of supply chain questions. What projector do I get? How do I integrate this with my project? You may have to talk to a CM or a specialized integrator to kind of help you get that hardware on board and working in the way that you want with the software that runs on the cameras themselves to capture depth. And additionally, it's very likely that you're going to want to end up getting Class 1 laser certification. And so this can be something that down the line can introduce a huge amount of delay into your project. While you may have most of everything figured out, you'll get to this sort of step where you need to get Class 1 laser certification, and realistically, there's requirements for it. You can fill out the report, do the tests, whatever is necessary. But now you're at the whims of a process that could take 3 months to complete, and your application is pending, and you can't ship your product until it is returned successful. And so knowing that, that is something that you have to plan for ahead of time. So if you are getting an emitter, you need to be kind of on top of this Class 1 laser certification if it's an eye-safe infrared emitter. If you have something that's not eye-safe, you have an additional 20 layers of bureaucracy that you're going to have to meet in order to be able to ship something that's not eye-safe. But I think for the purposes of what we're talking about here today, it's probably not necessary. Conversely, if your application doesn't need dense depth, maybe you just want to do some kind of photogrammetry, or you have a very sparse SLAM algorithm, or you're just trying to capture, optical flow in some way and do depth on that. You may not need an emitter at all. You may very well be able to just utilize the cameras as is and do some more software work to get good depth generated with sort of a low amount of texture in the scene. This is somewhat questionable, depends on kind of what you're trying to do. If you're aiming more towards something like a RealSense or a Luxonis, you're very likely to find that those cameras are sort of in the same application space as dense depth, especially in near ranges. If you're 1 to 5 meters, dense depth is probably easily achievable and fine. When you get to longer distances, of course, a projector doesn't do anything at all. And so, you may not need to get one in the first place. All right. And with that, we've mostly finished talking about hardware. The last thing that we need to talk about is HDR cameras. So HDR cameras are basically just regular cameras, and the way that they expand the dynamic range or sort of the color, like the difference in contrast in the scene, is by merging images with different exposures and synthesizing a wider range image, an image that has a much wider dynamic range. Unfortunately, if this is done in the embedded software, this often halves the frame rate because you have to take, at least 2 different images with 2 different exposures in a row. So if you're at 30 FPS, that now becomes 15 FPS of HDR images. Or if you're at 60 FPS, that's now 30 FPS of HDR images. And if you're not doing this in embedded software and you're trying to do this on the host itself, this can be computationally very expensive. And in fact, may not be ideal in practice, just purely due to the fact that you're going to be wasting a lot of your host's compute on just doing HDR, which could be otherwise effectively embedded onto the system itself. And with that, let's talk about a little bit more software. So once you get your hardware, that's great. We talked a lot about the trade-offs and different choices of what camera do you want to buy? How do you want to set up your baseline? Do you have a wide field of view, et cetera? But that only solves half the story. The other half is, okay, I have this camera, this hardware. Allegedly, we can plug it into a computer and it does things. But what are those things and how do we make the computer do it? And that's sensor streaming, sensor calibration, and depth map generation. And these are kind of the three components that I want to talk about today. So to start with sensor streaming, being at the whims of manufacturer software can be somewhat constraining. In particular, you have to ask yourself, like, what infrastructure does the software interoperate with? ROS1, ROS2, is it purely embedded? I'd pick on LibRealSense because it's sort of the common example, but what does this software do, and how are you able to work with it? Are you purely a ROS shop? Are you just doing stuff to spin up ROS nodes and stream from those and throw it into a pub subsystem? Or do you have a systems engineering team? Are they kind of building this as sort of an embedded device end to end for a pick and place system, for example, where the depth camera might be the only sensor on board of your robot? Maybe you don't need ROS for that application. And so you have to ask yourself, do we have a systems engineering team that's going to do that? For example, what happens if a sensor goes offline? This can happen for a variety of reasons. Cable comes unplugged, power goes out to some subsystem, something happens on the firmware of the sensor, something shorts, something melts because it's too hot. What happens to the rest of the system? And what you don't want, at the very least, is that if one camera goes offline, everything else crashes. And there's some resilience built into a lot of the software that we write day to day. Being in robotics, that's kind of a given. But especially with sensor streaming software, I've seen many examples where one sensor goes down and then it kind of cascades to every other subsystem. Or one sensor goes down and now the robot's spinning in circles because it thinks that it's got to find a left field of view when it only has a right camera. And lastly, like, what settings are you want to configure on this? And this is a bigger question to, like, do you need some kind of auto exposure? Do you need dynamic white balancing? Is there some kind of like ISO or other ISP settings that you need to set on this camera? These are things that you need to ask yourself if you're trying to talk about sensor streaming, because one of the things that kind of drives people away from these off-the-shelf solutions into doing this in the first place is that the manufacturer software doesn't work well. And so that is something that is going to be a big choice that you're kind of making upfront. Developing these sort of depth systems and getting your own hardware can sometimes be easy choices to make if your application is fairly standard. But fixing the software side of it's not always quite as simple. And in addition to that, you have integration challenges. Here at Tangram, we work in Rust specifically, but we also want to integrate with the rest of the ecosystems. That might include C and Python. So can your sensor streaming system support Rust, C, C++, Python? Where do you draw the line? In addition, you have concurrency questions. Are you taking some manufacturer's SDK and injecting it into your own multi-threaded concurrent program that you're kind of running ad hoc on the robot? Or is it some sort of separate multi-process setup? Do you have to worry about it at all? And in the case of ROS, it tends to be multi-process. And so maybe you kind of answer some of these questions just off the bat. But if you don't know this, you're going to have a real hard time figuring out when things are going wrong, which kind of leads to my last point here is visibility. A lot of manufacturer software doesn't really give you a lot of insight into how to debug or how to test these things. When something does invariably go wrong with a sensor somewhere, how do you figure out what went wrong? How do you figure out, what to test and how to test? And so that's kind of the gist of sensor streaming, right? There needs to be some process for getting images off these cameras. And once we have those images, then there's a lot of stuff that we can do. However, that has to somewhat be compatible with your downstream application. And that leads us to our next point, which is calibration. We might have all these images, we might have picked our hardware, but now we need an actual calibration because the depth map generation itself is going to be driven by the calibration process. And here at Tangram, we have kind of distilled calibration into three main topics. And the first two are kind of obvious. It's kind of what everyone talks about, whether you're OpenCV or some other project that does camera calibration. You have modeling the sensors, which is getting the intrinsics. and the registration problem, which is getting the extrinsics from camera to camera or camera to LiDAR, etc. And so if you have more sensors than just this depth camera, you want it to be calibrated to everything else in the system. But there's one thing that I've left out. Does anybody know what that is? You can post in the chat if you think you know. All right. Well, with that said, I will spoil the answer for you. But it's synchronization. One of the challenges with integrating, especially multi-sensor systems, and when you get into, combining cameras with LiDAR or cameras with IMUs or cameras with GPS, is that these might not always be firing at the same frame rate. You might have cameras at 30 frames per second. You might have LiDAR at 10 frames per second. And so you need to be able to know when things happen to get geometric consistency across the entire problem. And so part of what Tangram does as part of our calibration process is to sort of fully incorporate all three of these pieces for our partners when they come to us with calibration needs for depth systems that they've developed. And so here's just an example of kind of what the system could look like in terms of our visualization. This is much older than what it currently looks like and probably won't look like this in a month from now. But the general idea is that we're able to sort of visually verify what we see in terms of the system setup. So you can see there's 3 cameras at the top there. We also give a wealth of metrics and charts and other information to be able to verify that a calibration is, not only good, but also consistent. You're developing a production line, you're trying to develop your own depth. This is all going into sort of an end-to-end system. You don't want a process that's flaky like 50% of the time, just fails. And so this is why Tangram, when we built our calibration system, and that's really our bread and butter and has been for a long time, we wanted to make sure that we were providing a system that could inform a user when a calibration won't be consistent or when it's like, hey, this is good, but probably won't work the next time or may fail in certain scenarios. Aside from that, I'm not going to try and proselytize and sell you calibration tech too much. Actually, Daniel has asked distortion. I'm not sure what you mean by that. What do you mean by distortion in calibration? Distortion models. That actually goes under intrinsics. And so that'd be like the intrinsics of the sensor. You have some model that you sort of set the problem up to you. So that could be, a very standard OpenCV Brown-Conradi model, OpenCV fisheye. Tangram actually supports a wide variety of models. Not every calibration system does. And depending on whether you have like a wide vision lens, which is something we talked about earlier, you may choose to change your model depending on the camera, both on a per camera basis as well as kind of, what's the field of view, how much distortion am I expecting, etc. It's not shown in this slide here, but we do actually have distortion charts that demonstrate the distortion itself. Yes, we do have. The software also shows the distortion map, although that's somewhat of a secondary artifact. I am not displaying it on this screen, but if I did have time, I could probably try to find a calibration, run it, and then show that to you. Unfortunately, I'm not sure that I have that prepared today. All right, my last topic, and then I'll, get off my soapbox, but it's depth map generation. And so that typically is a downstream function of something that we call disparity matching or disparity matching algorithm. And there's a couple of different popular ones. And the 3 biggest ones that I've seen, at least in commercial sensors, are census matching, sum of absolute differences or SAD matching, and semi-global block matching or semi-global matching. And these kinds of algorithms have different effects, and which one you choose may be a function of how much compute you have to actually throw at depth map generation itself. So if this is happening on some embedded device, you may have some embedded CPU or some embedded GPU that you now want to run this on. These will all have different performance characteristics as algorithms. But two, depending on the kind of camera you have and what kind of artifacts you want to optimize for, you can see that you're going to get different results. So to start with, let's look at these two examples that I've captured on the right here. The bottom one is captured from a RealSense D435. You can see that this is basically the view that, if you can see my face talking, is kind of where I'm at today in my home office. And so there's the windows kind of on the side here. And then there's my face, which is in this sort of orange depth. You can see that there's a lot of holes in this depth map. So the holes in the depth map are places where we couldn't do any kind of disparity matching between both of the cameras. But you can see that the actual depth map itself is fairly smooth and fairly continuous. Contrast that with the scene above that, that sort of blue and teal green looking frame. And that frame is generated from a Luxonis Oak D-Lite, which, if I recall, does not have a projector or an IR emitter, and they use semi-global block matching. So one thing you can see in that picture above that you don't see on the bottom picture is that there's this sort of like hallucinated lines. You can kind of see these weird sideways lines that get hallucinated. That's an artifact of semi-global block matching, where if it doesn't have very high texture or contrast in the scene, it can kind of simulate this sort of false depth that isn't actually there. And so unlike something like a RealSense that does not use semi-global block matching and does have an IR projector, sometimes your depth can actually be much worse as a result of choices you've made earlier, either dependent on the algorithm you've chosen or independent of the algorithm that you've chosen. And so all of this probably sounds like a lot. We've covered a variety of topics, from hardware selection to supply chain to baseline generation and simulations of what kind of error can we expect and how do we expect this to operate down the line. And a lot of these decisions that I've talked about can kind of be a little scary, because they're the decisions you make early that affect you extremely affect you to an extreme amount down the line. But that being said, I wanted to say Tangram can help with all of this. So whether it be camera selection, baseline determination, we know how to run these simulations. We've done this before. We have experience in building sensors and sensor systems. And so we have the tools to know it matters. Additionally, we build streaming software and we do build calibration software. So if you're interested in that and you're interested in being able to kind of run that with your own system, you should talk to us. With that, I will stop trying to sell you guys too hard, and I'll say thank you so much for taking the time to watch this webinar today. Thank you so much for taking the time to listen. You can always contact me at my email here, but for the time being, I think Adam needs to jump off. So I am going to try and take some questions if everyone's good to go with that.